Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when values of transmission line parameters are given. We shall also learn how to compute percentage voltage regulation of this line using those constants when load details are given. A three-phase 50 Hz 100 km long transmission line has following constants per kilometer per conductor. Resistance equals to 0.25 ohm, inductance equals to 2 millihenry and capacitance equals to 0.015 microfarad. Using nominal T method, we have to calculate the voltage required at the sending end in order that a load of 10 megavolt ampere at 0.8 power factor lagging may be supplied at 120 kilovolts. We also have to compute the sending end input power and the percentage voltage regulation at the receiving end. Let us now write down the given data. Load SL equals to 10 megavolt ampere, that is equal to 10 into 10 to the power 6 volt ampere. Line to line receiving end voltage, here line equals to 120 kilovolts, that is equal to 120 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase, VR equals to VR line divided by root 3, that is equal to 120 into 10 to the power 3 divided by root 3, that gives us 69,282 volts. Given load power factor cos phi L equals to 0.8 lagging, let us now determine power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 10 into 10 to the power 6 divided by root 3 into 120 into 10 to the power 3. That gives us 48.1125 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 48.1125 ampere at an angle minus 36.8699 degree. In this case, load current IL equals to receiving end current IR. Given length of the transmission line D equals to 100 kilometers. Resistance per kilometer per phase R1 equals to 0.25 ohm. Inductance per kilometer per phase L1 equals to 2 millihenry and capacitance per kilometer per phase C1 equals to 0.015 microfarad. Let us now calculate resistance per phase R equals to R1 into D. Using values we get 0.25 into 100, that gives us 25 ohm. Inductance per phase L equals to L1 into D. Using values we get 2 into 100, that gives us 200 millihenry or 0.2 Henry, and capacitance per phase C equals to C1 into D. Using values we get 0.015 into 100, that gives us 1.5 microfarad or 1.5 into 10 to the power minus 6 farad. Now we shall calculate inductive reactance per phase. XL equals to 2 pi f into L. Given supply frequency f equals to 50 Hz. Therefore, XL equals to 2 pi into 50 into 0.2. That gives us 62.832 ohm. And capacitive susceptance per phase DC equals to 2 pi f into C. Using values we get 2 pi into 50 into 1.5 into 10 to the power minus 6. That gives us 4.71 into 10 to the power minus 4 mho. Now we shall determine series impedance per phase of the transmission line. Z equals to R plus JXL, that is equal to 25 plus J times 62.832 ohm. This may be written in polar form as 67.623 ohm at an angle 68.3 degree. And shunt admittance per phase Y equals to J times BC, that is equal to 0 plus J times 4.71 into 10 to the power minus 4 mho. This may be written in polar form as 4.71 into 10 to the power minus 4 mho at an angle 90 degree. We have obtained series impedance per phase of the transmission line Z equals to 67.623 ohm at an angle 68.3 degree, and shunt admittance per phase Y equals to 4.71 into 10 to the power minus 4 mho at an angle 90 degree. Let us now calculate Y into Z. Using values we get 4.71 into 10 to the power minus 4 at an angle 90 degree into 67.623 at an angle 68.3 degree. That gives us 0.03185 at an angle 158.3 degree. This may be written in Cartesian form as minus 0.029593 plus J times 0.0117764. Now we shall compute 1 plus 1/4 of Y into Z, that is equal to 0.9926 plus J times 0.002944. This may be written in polar form as 0.9926044 at an angle 0.1699 degree. For nominal T equivalent circuit, A equals to D equals to 1 plus half of Y into Z, that is equal to 0.9852 plus J times 0.00589. This may be written in polar form as 0.9852176 at an angle 0.3425 degree. B equals to Z into 1 plus 1/4 of Y into Z. Using values we get 67.623 at an angle 68.3 degree into 0.992644 at an angle 0.1699 degree. That gives us 67.123 ohm at an angle 68.4699 degree, and C equals to Y, that is equal to 4.71 into 10 to the power minus 4 mho at an angle 90 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 69,282 volts at an angle 0 degree. We have determined receiving end current IR equals to 48.1125 ampere at an angle minus 36.8699 degree, and generalized constants for T equivalent circuit A equals to D equals to 0.9852176 at an angle 0.3425 degree. B equals to 67.123 ohm at an angle 68.4699 degree, and C equals to 4.71 into 10 to the power minus 4 mho at an angle 90 degree. Expression for sending end voltage per phase Vs equals to A times VR plus B times IR. Using values we get 0.9852176 at an angle 0.3425 degree into 69,282 at an angle 0 degree plus 67.123 at an angle 68.4699 degree into 48.1125 at an angle minus 36.8699 degree. That gives us 71,007.241 plus J times 2100.2152 volt. This may be written in polar form as 71,038.294 volt at an angle 1.6942 degree. And expression for sending end current per phase Is equals to C times VR plus D times IR. Using values we get 4.71 into 10 to the power minus 4 at an angle 90 degree into 69,282 at an angle 0 degree plus 0.9852176 at an angle 0.3425 degree into 48.1125 at an angle minus 36.8699 degree. That gives us 38.0904 plus J times 4.4182 ampere. This may be written in polar form as 38.3458 ampere at an angle 6.6143 degree. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase on no load VRO equals to Vs divided by A. Using values we get 71,038.294 at an angle 1.6942 degree divided by 0.985276 at an angle 0.3425 degree. That gives us 72,104.167 volt at an angle 1.3517 degree. Let us now determine voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 72,104.167 minus 69,282 divided by 69,282. that gives us 0.0407 per unit or 4.07%. We have computed sending end voltage per phase Vs equals to Vs at an angle delta equals to 71,038.294 volt at an angle 1.6942 degree, and sending end current per phase Is equals to Is at an angle phi 1 equals to 38.3458 ampere at an angle 6.6143 degree. For star connected system, sending end current per phase equals to sending end line current, and line to line sending end voltage Vs line equals to √3 times Vs, that is equal to √3 into 71,038.294, which is approximately equal to 123 into 10 to the power 3 volts or 123 kilovolts. Phase difference between Vs and Is, phi s equals to phi 1 minus delta. Using values we get 6.6143 degree minus 1.6942 degree, that gives us 4.9201 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 4.9201 degree, that gives us 0.9963 leading. Now we shall calculate sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 71,038.294 into 38.3458 into 0.9963, that is equal to 8.142 into 10 to the power 6 watts or 8.142 megawatt. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine generalized constants A, B, C and D of a three-phase medium length transmission line based on its nominal T equivalent circuit when values of transmission line parameters are given. We have also learned how to compute percentage voltage regulation of this line using those constants when load details are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.